Hello guys, welcome back to another AIME problem solution video. Today we have yet another problem here, and as always, to start off by first reading the question. So, find the least positive integer n such that when 3 to the power of n is written in base 143, its two rightmost digits in base 143 are 0 and 1, or 0, 1. Now I'm first going to write out something which is that 143 is going to be equal to 11 times 13. And we will be using this later on. So now, given this current information, I can actually write a new equation which is that 3 to the power of n is going to equal to 1 modulo 143 squared. And this is because we're writing in base 143, and we are using the first two digits, so 0 and 1. So this would be the second digit squared. So now that 3 to the power of n should end with 1 modulo 123 squared. Now from this I can separate this into two further cases, which is that 3 to the power of n is going to be equal to 1 modulo 121, or 11 squared, and also 3 to the power of n is going to be equal to 1 modulo 169. Now I'll start off with the easier one, which is 3n is going to equal to 1 modulo 121. Now for this case, we can just write out what n is going to be equal to from 0, 1, 2, 3, 4, and so on. And the list we get that the modulo is going to be equal to 1, 3, 9, 27, 81, and then it leads back to 1 and 3. So now our cycle is going to be 5, so we know that n is going to have to be equal to 5k for it to be equal to 1. Now let's go on to our second case, which is that 3n is going to be equal to 1 modulo 169. Now for this case to be satisfied, we need both of these cases to be satisfied as well. So now we're going to solve this in a similar way to this one. Now for 169, it's a little bit more complicated, as we can't really just do the same things before, where we plug in a bunch of numbers, as this one is a lot more bigger. So we can observe something, which is that 3 to the power of 3 is going to be equal to 1 modulo 13. Somehow we need to somehow apply this into this one here. Now we can see that 3 to the power of 3 here is going to be equal to 13, let's say a, plus 1. Now we can plug this into this one here. So let's say 3 to the power of 3 to the power of, let's say another new integer, b, is going to be equal to 1 modulo 169. And then I can also rewrite this into 13a plus 1 to the power of b, and it's going to be equal to 1 modulo 169. And we also need to satisfy that b is going to be equal to 0 modulo 13. And I'll sort of break this down really quickly. Now as you can see here, this should be equal to 3 to the power of n. And I've basically just replaced it with 3 to the power of 3 to the power of b to equal to this. And now we can sort of solve this, knowing that b is going to have to be equal to modulo 13 as well, as b is going to equal to 0 modulo 13. Now from this we can just sort of plug in what b could be, so 0, 13, and 26. Now obviously b can't be 0, as we can't have n equal to 0. So we have b equals to 13, and after plugging in, you'll see that it works. Now that we know that b equals 13 works, we can see that n should equal to 3 times b. And since we know that b is going to be 13, and obviously since b needs to be smaller, to be as small as possible, for n to be as small as possible, we have n is going to be equal to 3 times b, or 39. So our cycle is going to be 39, so it repeats every 39 numbers of n. So I can rewrite this into n equals 39, let's just say p. Now we need n to satisfy both of these, as I just said, so n has to be the least common multiple of 39 and 5. And since there isn't any common divisors between them, it's just going to be equal to 39 times 5, or 185, sorry, not 185, 195. So the answer to this problem should be 195. Thank you guys for listening. If you any of these has a problem, please dump down in the comments, and thank you guys for listening. Bye.